Hello everyone, my name is Mohsen. This is joint work with Ali, Yadollah and Taher. Together with Ali, we'll present this work. This talk is about quantifying global token attribution by incorporating the whole encoder layer in transformers. Let's first talk about the goal of quantifying token attribution. Current pre-trained language models rely on an attention mechanism to mix input tokens. We want to know how much each token contributes to the model's final decision to better explain the model's behavior. For instance, here we have the sentence "a deep and meaningful film," and the model should decide whether the sentence is positive or negative. Intuitively, we expected to pay more attention to positive words like meaningful. In this work, we introduce a novel token attribution analysis method to quantify these attributions accurately. The simplest element for quantifying the token attribution is leveraging the attention weights assigned by the self-attention mechanism itself. And if we plot it in one of the layers, it will look like the heat map on the right. It shows how much a token in a row attends to other tokens in columns, including itself. However, there have been debates on whether raw attention weights are reliable anchors for explaining the model's behavior or not. In the paper, attention is not only a weight, it is debated that we need to consider the vector norms as well. For example, suppose a vector representation has a large norm. In that case, the self-attention mechanism might assign a small attention weight to compensate for the large norm, but not because that representation is less important, and also vice versa. So it is suggested to take the norm of each token after multiplying it by the attention weights, and that this measure will be more reliable than the raw weights. Back to the raw attention weights, if we plot its attention matrix, it will be as shown on the right. And if we consider the vector norms, the results will change this way. We will later elaborate on how we investigate if this change has really made a positive impact, but note that this norm-based map is actually a better map than the previous weight-based one. Even though using vector norms seems promising, the multi-head attention component is only a part of the whole. It is just one component of the attention block. And in a consecutive paper, the residual connection and the layer normalization after the multi-head attention are also incorporated into the analysis. Moreover, the diagonal of the attribution matrix in this method interestingly demonstrates that the model tends to preserve each token by attending to itself more than mixing it with other tokens. Now we will explain our contributions and the method we introduced as GlobEnc. First off, we should note that the attention block is not the whole encoder block in transformers. The transformers encoder architecture includes a feed-forward layer, a second residual connection, and a second layer normalization on top of the attention block. In this work, we also incorporated these parts, except for the feed-forward network, which does not have a simple decomposition and its effect is incorporated indirectly. The enc in GlobEnc comes from incorporating the components up to the encoder layer's output. Additionally, all the previous methods were for quantifying the token attribution in only a single layer. In this work, we extended this to all the layers and used a method called rollout for propagating single layer attributions throughout layers. Here we have an example of the rollout method. For calculating the attention of the sync token in the top right to the source token in the bottom left corner, we recursively combine the attribution weights along all available paths. This will allow us to find the essential tokens for the whole model rather than single layers. And the globe part in GlobEnc is actually referring to this global analysis.
Hi, I'm Ali, and I'm going to continue the presentation from here. In our experiments, we measure each token's contribution using a gradient-based saliency method. Then, we evaluate each of these analysis methods that are based on including or not including one or multiple components, or even by changing the weight basis or norm basis of it. In each method, we extract their corresponding attribution map in each layer and apply rollout to all the layers to have an aggregated result. Since the classifier is using the CLS token representation of the final layer, we use the CLS attribution values to all tokens as the contribution scores. Finally, as an evaluation metric, we report the Spearman correlation between the computed contribution scores with the gradient-based saliency scores. Here we present to you our results on different analysis methods. First, we observe that the norm-based attribution methods are superior to the weight-based ones. This shows the importance of using norm-based methods instead of using raw weights, even when aggregating all layers. In this comparison, we can see that including the residual connection to the norm analysis significantly improves the results. However, by adding the first layer normalization component inside the attention block, we face a detrimental effect. Interestingly, the result recovers and also improves by incorporating the second residual connection and the output layer normalization. One of the main and effective elements inside a layer normalization component is its scaling weights. The majority of these weights are close to 1, but as shown in the figure, these are some outliers. In some studies, these outliers have been shown that are highly influential in the model's behavior. As an interesting observation, the outlier weights of the two layer norms seem to be the opposite of each other. By using Pearson correlation and having large negative values as a result, we can confirm that this diametric pattern exists within all BERT layers. Therefore, it is necessary to add both layer norms to cancel out each other, or while we could end up with corrupted results. In the end, we can see that GlobEnc provides the most promising results in all three tasks. In addition to the quantitative results, in this slide we demonstrate multiple analysis methods attribution scores throughout the model on a sentence selected from the SST2 dataset. As you can see here, each component has its own effect on the resulting scores, and GlobEnc provides the most plausible one in the final layer. Here, I'm also excited to share with you our Colab demo. You could try out GlobEnc with the notebook provided in our GitHub repository online. You can give any checkpoint of language models such as BERT or Electra and see which tokens are more important for it in any sentence. Thanks for your attention, and please do not hesitate to contact us in case for any questions.